I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on Ampere's Circuital Law for the course Electromagnetic Fields and Waves. So before going to see the topic, we see a recall of the previous topic, magnetic field due to a circular conductor. So in a circular conductor, whenever there is a current flow, a magnetic field is generated and the generated magnetic field is calculated by the formula B of Z is equal to mu naught I A square divided by 2 into A square plus Z square power 3 by 2. So from this equation we can understand that the magnetic field of a circular conductor depends on the current flow through the loop and also the distance and the radius of the loop. So learning objective of today's video is understanding the fundamentals of Ampere law. So we see the mathematical relationship, how the magnetic field is related to the current. And also we apply circuit analysis. We use the concepts of integration techniques and symmetry principles for calculating the magnetic field intensity through this current carrying conductor. And the extension of today's topic is exploring the real world applications like practical electromagnetic devices, solenoids, toroids, and also the transmission lines. So we discussed the topic in a design thinking way. So in a design thinking, the empathy part. So in the empathy part, we see the historical context of Ampere's law. So Ampere's law was formulated in 1826 by Ampere, and he formulated after observing how electric currents create the magnetic fields. And his work was based on Ørsted's discovery that a compass needle deflects near a current carrying wire. And this fundamental principle explores the understanding of electromagnetism, and also it forms the groundwork for Maxwell's equations, because one of the Maxwell's equation is formulated from the Ampere's law. Now, in the design thinking define part, we are identifying the core concept. We can define the statement of Ampere's circuital law as the line integral of the magnetic field intensity around any closed path equals to the total current enclosed by the path. And it is given by I integral over the closed path h dot dl is equal to I enclosed. So from this expression we can understand that the magnetic field intensity depends on the current flowing through the conductor and also the length L. So dl is the differential length, H magnetic field intensity, and I is the current flow through the wire. So now we are visualizing the magnetic field around a conductor. So when there is a current flow, there will be a magnetic field generated and it will form a concentric circular lines around the conductor. And the direction of the current is upward current through the wire, and field intensity decreases whenever the distance increases from the wire. So the field intensity is inversely proportional to the distance. So when the current flow through the straight conductor, concentric circular magnetic field forms around it, and it is given by the expression H is equal to L divided by 2 by R. And now coming to key applications of Ampere's law, the real world applications we see in the design thinking ideate part. So it is useful in calculating the magnetic field of a solenoid and also toroid. In a solenoid, the magnetic field intensity can be calculated, and also the toroid, the magnetic field intensity distribution in circular coil configurations is found. And if we see the coaxial cable, we can analyze the field confinement between inner and outer conductor of a coaxial cable for signal transmission by using this Ampere's law. Finally, we take transmission line. In the transmission line, we can understand the electromagnetic field pattern between the parallel conductors which carry the opposite current. So this slide explains the key applications of Ampere's law. Now, in the design thinking part of prototype, we see the problem solving strategy. In the problem solving strategy, the first step is to identify the symmetry of the geometry. So the geometry, whether it exhibits circular, cylindrical or planar is determined. And after determining the symmetry, we choose Amperian path. So Amperian path is a closed path where the magnetic field is constant or zero along the segments. And after finding the Amperian path, we apply the integration to evaluate the magnetic field by using the formula integral over the closed path h dot dl is equal to the current enclosed I. So, key takeaways from this video. First, we have seen the core principle, the Ampere's law fundamentals and its relationship between the current and the magnetic field. And after that, we use the mathematical calculation of this Ampere's circuital law based on the symmetry of the geometry we have taken. And engineering impact we have analyzed, we have seen the real world applications, and in the broader context we have seen how the Maxwell's equation is derived from the Ampere's circuital law. And next is summary. So in the summary, so far we have discussed Ampere's law and its fundamental statement, historical context, and the magnetic field characteristics. We have seen that there will be a concentric circular lines and its magnetic field intensity variation, and also the direction of the current flow in a current carrying conductor. We have seen various key applications and the problem solving strategy. We have seen how to uh, calculate the magnetic field using Ampere's law for symmetrical distributions. And finally, we have seen the impact and also takeaways. Thank you.